Hi everyone. In this lecture, we're going to be looking at the gamma distribution. It's another special distribution for continuous data. So far, we've had a look at the uniform distribution and the normal distribution as special cases. Both of these assume that your data is symmetric, but in real life, you have a lot of instances where your data is not symmetric, so it's skewed. So for instance, you have a graph like this. This is a typical gamma distribution. And what it represents is you have a large proportion of your population lying in this region here, and then fewer and fewer and fewer as you go further away from that. So a good example is personal income. You're going to have a lot of people in a certain range, probably, most likely. And then we know that as people, as you, income gets higher and higher and higher, there are fewer and fewer people who earn very, very high figures. So this would be a typical graph for such a distribution. And these are two other examples that you can also take a look at. Before we look at the gamma distribution itself, we're going to have a look at the gamma function. So this is what the gamma function looks like. So we use a capital letter gamma, and then alpha is just some value greater than 0. And this is what it looks like, but there are some very useful properties that makes it easy for you to calculate. And we'll test you probably on more on the properties. You won't have to integrate this thing. The first property we're going to consider is this first one here. You can see that gamma alpha is just the same as alpha minus 1 times gamma alpha minus 1. And note, well, this value of alpha, it doesn't have to be an integer. It can even be a fraction as well. So just remember that. It will come in handy a bit later. And this one, I think you already know that gamma n is just n minus 1 factorial. Gamma 1 is equal to 1, and this is another special case that gamma half is equal to the square root of pi. So these are just important properties that you need to know. So I'd like you to apply those properties and see if you can work out these questions. So this is the first exercise of 4. Now we're going to have a look at the gamma distribution now. So this is what a gamma distribution looks like. It takes two parameters, alpha and beta. And this is how you're going to write it shorthand. Alpha is always first, followed by beta. Alpha is referred to as the shape parameter. Beta is referred to as the scale parameter. Both of these values are absolutely any values, even fractions, that are greater than 0. So now to show you why they are called shape and scale parameters, we're going to have a look at a few examples. So in this example, beta is fixed and then alpha is varied. Beta is set to be equal to 1, and then we have a look at alpha equal to 1, and you see this first curve that you get here, which has a different shape to when you have alpha equal to 2, which is also different for alpha equal to 4. So which one you're going to use in practice just depends on what your data looks like. So you'll just plot your data in practice, and then you'll get a good idea of maybe which graph works best in that case. In this graph, the alpha parameter is fixed to be equal to 2, while the beta parameter is allowed to vary. The beta parameter is called the scale parameter because values other than 1 either stretch or compress the PDF in the x direction. So if you focus on this beta equal to 1 function, we'll compare the other two with that so you can see what that means. So if you take beta equal to a third, you end up with this more compressed version. And if you take beta equal to 2, you end up with this more flattened one, but it's more stretched out. Now, the gamma distribution is unique. Just as with the normal and the uniform, a distribution function is absolutely unique. So these examples are based on that concept, and I would like you to try these exercises. They are typical questions you can expect to see in a test or in an exam. Now, there are special distributions that can be derived from the gamma depending on your choice of alpha and beta. So I'm just going to put them here and we'll go in a little bit more detail a little bit later. So firstly, suppose you take y to be a gamma distribution with parameter alpha, beta, and alpha is such that it's equal to some value, nu, so that's just spelled like nu, but it just represents an arbitrary value, which is an integer greater than 0. If you have alpha equal to nu divided by 2 and beta equal to 2, then the result is what is called a chi-square distribution with parameter nu. So this is how it's going to look. So this is how you write chi-squared under the shorthand notation. The chi-squared distribution only takes one parameter, which is just like this one. So naturally it's also a skewed distribution, but it's just a special case of the gamma. Another special case of the gamma is if you fix alpha to be equal to 1 and then you take beta to be some value 1 over lambda, and lambda represents any value that is greater than 0. So if you select parameters that have those settings, then you have what's called an exponential distribution with parameter lambda. Just excuse that error, you can fix it for yourself. And this is how you write the shorthand notation. EXP, short for exponential, and then lambda because it only takes one parameter. Now there's a very special case that is important to us. How about beta equal to 1? Beta equal to 1 gives you your standard gamma distribution. Just like with your normal distribution, if you have a mean equal to 0 and a variance equal to 1, you have a standard normal. Here, if you fix beta equal to 1, doesn't matter what alpha is, the moment beta is equal to 1, you have what's called a standard gamma, and this is what the PDF looks like. So if you literally go and substitute 1 everywhere you have a beta, you'll find that you get this function directly. So you can check that for yourself. This is what standard gamma density curves look like. So this graph is there in the textbook, and what they've done is they fixed beta to be equal to 1, and then they varied your alpha. So you can see that the shapes differ, which makes sense because alpha is your shape parameter. Now, when x is a standard gamma random variable, this would be your shorthand notation. This is going to be 1. And the CDF is a special one. It looks like this, and it's called the incomplete gamma function. Now, just like with the normal distribution, you're not going to do any integration when you want to find probabilities. You're going to use tables. So somebody has already got and plotted tables for the incomplete gamma distribution. That's just the CDF of a standard gamma. And this is what the table looks like. At the back of your textbook, you will find table A4. It's titled the incomplete gamma function, and it simply gives you left-hand probabilities for a standard gamma. So remember, beta is fixed to be equal to 1. So therefore, you can only use this table if you have a gamma distribution where beta is equal to 1. The top row here gives you the different values of alpha that you could have. And then the far left-hand corner are just the values of x. So in other words, it's this lowercase x. And then all these values inside the table are your probabilities. Okay, let's have an example so we just see how to read the tables. So let's start off with A. Suppose x follows a gamma distribution with alpha equal to 3 and beta equal to 1. Now immediately you can see that your value of x is 2 and your value of alpha is 3. So you're just going to go to the table and you're going to look for those things. You look for alpha equal to 3, x equal to 2. You want the area to the left of 2. So similar to a normal table, you go across and down, and in this example, you end up at 0.323. So this is how you'd complete this one. This notation here, they use it in the textbook, so this is pretty much what it means. So it's just another way of writing the CDF. So you put a semicolon and then afterwards you just give the relevant parameters. Because it's a standard gamma, they don't bother putting in the 1. That's why there's only the alpha in this case. So you can have a look at the other examples. You follow the same procedure. Have a look and see if you get these answers. And there are more examples in the textbook. See example 4.27. Now, what if y does not have a beta equal to 1? Well, just like with the normal distribution, we have a transformation that we're going to use. So whatever that y value is that we have, we're going to divide by beta, and then immediately the result is a standard gamma. So this is what it looks like more formally. If fy is the CDF of y, which is a gamma alpha beta, and if we let fw be the CDF of y over beta, so that's just a gamma alpha 1, then suppose we wanted to find a left-hand probability. This is how we'd proceed. So the probability of y being less than or equal to y is just this by definition. Now we divide both sides by beta. Remember with the standard normal, you standardize by subtracting the mean, dividing by the standard deviation. Here it's a similar concept, but this time you divide both sides by your beta. Now you know that W is just Y over beta, which is a standard gamma, and you can find standard gamma values in the incomplete gamma tables. So all I simply did is replaced the Y over beta with W because it's just the same thing from there. And what this relationship is telling you is that if y of y is equal to fy over beta, but on that W scale. So that's on the standard gamma. So we do have tables for the standard gamma. So you're going to look for y over beta if you want to find probabilities there. So in a nutshell, this is the result. Let's have a look at an example. In this example, in all of the cases actually, all of the betas were selected to be different from 1. So let's have a look at part A. So x is not standard gamma, but we know that if we divide by the shape parameter beta, then we end up with a standard gamma. So this is using the textbook notation here. So before I go to the next line, it's just this. So instead of just having one parameter, they have both of them because it's a non-standard gamma. So that's all that it means. Everything after semicolon is just your parameters. So we've been told that alpha is 4 and beta is 2, and we want to find the area to the left of 2. But since this is non-standard, we're going to divide that 2 value by beta, which is equal to 2. So you end up with f1 for 1. So I could have just written f1 semicolon 4 because it's now a standard gamma, but I wanted to just demonstrate clearly what just happened. So now we have a standard gamma. So we want to find the parameter 4, which is your alpha, that one. And then we need to find 1. And then you go across and down and you end up with 0.019. And that's how you get that answer. So you're going to follow a similar procedure on the other ones. You just divide everything by your beta, and then you can read those values from your standard incomplete gamma function tables. In the textbook, there's also example 4.28, which demonstrates how you do this. Now, what if I asked you to find a percentile? It's very similar to what you do in the normal case. You're going to find a value on that standard gamma scale, and then you just work backwards and you convert it to the gamma distribution you're interested in. So let's look at an example. This example wants you to find the 90th percentile, or in other words, a value of C such that the area to the left is 0.98. Now, we know that if we take x and divide it by its beta, you end up with a standard gamma. So specifically in this case, x divided by 2 is a gamma 6, 1. Okay, so the 2 becomes a 1, and automatically the whole thing is a standard gamma. And you can find these probabilities in the table. And remember, we proved this already, but we know that the area to the left of C on the x scale is the same as the area to the left of C over 2 on that W scale. So we can now look for this C over 2 in the tables. So what value is such that the area to the left is 0.98 on the W scale? Here, remember the table gives you alphas. Beta is assumed to be 1. So you look for your alpha. In this case, it's 6. So you go to your 6 column. And then now when you're in this column, now you need to find that probability of 0.98. So these are all left-hand probabilities. So if you go and you look for 0.98, you're going to find it over there. And then remember, you want to go backwards and find a value of x. So you go across in this case, and you end up at the value of 12. So in other words, you can take this right-hand side and you can rewrite it as follows. So we know that this w less than or equal to c over 2 is just this. Okay, so 12 is exactly the same as that C over 2, because I know the area at the left of 12 is 0.98. So if I focus on those two things, I know that 12 is equal to C over 2. Therefore, if I solve, C is equal to 24. So you've just pretty much done the opposite of that standardization. Instead of dividing, here you're just multiplying. So you can think of it as going backwards. This is the moment generating function of a gamma random variable. In the textbook, they show you the proof, but you do not need to be able to prove it. So don't worry about it. However, you need to be able to show that the mean and the variance are equal to alpha beta and alpha beta squared, respectively, using the moment generating function as is, or using that RXT function. So just make sure you can do that calculation. And then the last exercise that I would like you to attempt is this exercise 4 on exercise in the textbook on page 201. All right, we have reached the end. All the best.